Well, good morning on this nice overcasted day in sunny Southern California. How you doing, team? We are cranking along in reactions and solutions. So let me see what video we're on here. Looks like video 6. Trying to keep it in some semblance of order, right? Titrations. So we've looked at, precipitation reactions, acid-base reactions, and the key here is acid-base reactions. So we looked at how to, predict the products, balance them. We can look at the molecular complete ionic net ionic equation. But usually for titrations, we're going to be doing stoichiometry, especially in lab when you put it's a pretty classic undergraduate laboratory to work on those titration skills with the burette. So we just had the video, and if you need to review it again on the techniques from lab, so look at the theory from the last video we just did in video 5, but definitely review any videos that are available from your professor for how to perform titrations accurately, right? Knowing it in your head is a lot different than being able to do it with your hands. I've seen a big disconnect with a lot of people, and it's important. That's why we have labs, right? So we can connect the knowledge and theory in your brain to you being able to perform this in your lab and see that connection and go, wow, that stuff actually works. Plus, out in the real world, you got to be able to do stuff, right? So either you'll get live demonstrations, elbow to elbow, or videos, or both preferably, which is great. So let's look at the calculations involved in doing titration calculations. And we're going to stick with just acid-base titrations. We'll find out later when we look at redox reactions. We could also do redox titrations, electron transfer, but we're going to focus on proton transfer for acid-base reactions. So review the last video on, what's an endpoint, what's an equivalence point, all those kinds of things, what's a burette, yada, yada, yada. Let's look at the different types of calculations. There's not many different types of calculations we're going to do, but really only fundamentally 2 that typically you'll see. So the first one, by far the most common in lab, is you're going to figure out the concentration of an unknown. Now, it may be a known unknown, and your professor says, hey, here's the concentration. Let's do your titration and see if you can get it. So practice, right? That's the way we like to teach lab. We show you how to do it. We give you a known unknown so you can see if your technique is correct. Are you precise? Are you accurate? Do you have any kind of systematic error? All that fun lab stuff. That's why we have lab videos and lab performance for skills. So we want to figure out that concentration. Now, obviously in lab, once we have confidence in your technique, then we'll give you a true unknown. You have no idea what its value is. So here's some acid. What's its concentration? I don't know. So you titrate it with a known standardized base. A standardized meaning its concentration. So that's the first one. Get the concentration of whichever one is unknown. One will be known, the other will be unknown. So we can figure them out pretty fast. The second one, which is more usually done by your professor ahead of time. So when you've got your burettes can only hold up to 50 milliliters of titrant, right? The solution that goes in the burette's called the titrant. Well, you don't want to have like an unknown acid and start draining out your base titrant, and then fill it up towards the top, and you get down towards 50, and you still haven't had the indicator change color. You're, oh crap moment, professor, what do I do? See if you forgot your indicator, and if it looks like everything's good, that means we didn't calculate the amount of base needed to titrate that particular acid properly, because you don't want to drain out your burette, have to refill it and keep going. That's just too many measurements. I mean, it's doable, but it creates a lot of error. So ideally, you want to use somewhere in the 25 to 40, 45 milliliter range. You don't want less than 10 milliliters because that gives you fewer significant digits. So we want at least 10, but preferably down in the 25 to 45 range. So we calculate ahead of time, anticipating how much of this titrant we're going to need. And that's this type of calculation, right? So if I give you 25 milliliters or 30 milliliters of an acid of a known concentration, you don't know its concentration, I do, right? I can calculate the volume of the base titrant needed. And so we know we don't have those kinds of problems. But you may have to do that in the real world, right? If you move up and on your own, you'll have to do those kind of calculations on your own. So let's do a couple of these, and I'm going to show you some interesting shortcuts too. I don't give you a lot of shortcuts, but when we're using concentration units, I'm going to show you a way to skip 2 steps in your unit line equation calculations. Optional. In lab, I'll force you to do that so you get used to it, because if you're uncomfortable with it, the more you do it, the more comfortable it becomes. It's amazing how that works in every aspect of your life. And then I'm going to show you another cool trick using equivalence. Since we learned what normality and equivalence are extremely useful for acid-base titrations because of the way they react. So let's look at some example problems and we'll slip the shortcuts within. All right, this is the kind that I would probably do when I'm designing a lab or something, right? So let's say I have some 0.1058 molar phosphoric acid solution. And I'm like, okay, hey, let's make that an unknown and have you guys titrate it. Well, let's say I want 25.00 mils or something. We could, measure that out pretty easily. Our students could. Well, how much? Let's say I have a 0.2410 molar sodium hydroxide solution we're going to use as a titrant, right? Well, what volume of that would I need? So and if it's too much, if it's beyond 50, I'd have to adjust this number to make sure that the students use less than 50 milliliters, preferably the 25 to 45 milliliter range. But this is a problem I could give you, pretty straightforward. So what volume of this 0.2410 molar sodium hydroxide solution is required to titrate, right? Get to that equivalence point, 25.00 milliliters of a 0.1058 molar phosphoric acid solution. So without using shortcuts I'm going to show you later, we're going to need to know the mole-to-mole ratio between the acid and the base, right? If we want to do the stoichiometry, we got to convert from the acid to the base. That requires the mole-to-mole ratio from the balanced chemical equation. I'll show you a shortcut later where we can bypass that. It's pretty cool. So let's do that first, and then we'll just apply. We're not using any new knowledge. This is something we already know how to do. We're just applying it in stoichiometry to acid-base reactions. That's it. So if you need to review stoichiometry videos, go for it. But this should be pretty easy to set up. Let's take a look at the equation. So we've got sodium hydroxide. Everybody agree? Well, that's a strong base. And since that's a strong base, it doesn't matter if the acid is weak or strong. This is going to go to completion. All right. As long as one or the other or both are strong, boom, 100%. So let's react that with the phosphoric acid molecules that are the solute, right, floating around in water there. We're going to get the, remember, double displacement. The OH minus from the base and the H plus from the acid give us water. You get water plus a salt. And the salt will be sodium phosphate. So sodium's a +1, phosphate's a -3, so we need 3 sodiums to balance that. So Na3PO4. Now, if you look on your solubility chart, we already know by now sodium salts are always soluble, right? So we're going to put an AQ there, and of course the water's a liquid. Let's balance it. We're going to need, we got the 3 sodium, so we're going to need a 3 here, which means we're going to need, we got 3 6 hydrogens, so 3 times 2 is 6, so boom! And I'm going to show you, look at the time we spent doing that. The shortcut I show you later, if we relate the acid to base by equivalence rather than moles, we can skip that balanced chemical equation. Wapa-ching, wapa-choo. Pretty nice. Let's do our game plan. You ready? We've got, which one are we solving for? Volume of base, correct? So we're solving for this, which means we're starting with the acid. So if you're solving with anything for the base, volume or concentration, start with the acid. If you're solving for the acid, whether it's the volume or the concentration, start with the base. Start with the other species. So I get a lot of students, I don't know how to start the problem. What are you solving for? Start with the other thing, right? So we're solving for the base, so start with the acid. I don't start with concentrations. That's a conversion factor to convert solution to solute units. So start with the volume of the acid. So we're going to go milliliters of the acid solution. And we, now remember, the molarity is moles per liter. So, and I'm going to show you 2 ways to do this. So first, we got to convert that to liters. And then we can go to moles of H3PO4. See that? We've done that before. Once we're in moles of H3PO4, we can go to moles of sodium hydroxide. And what's, we've got the molarity, right? We can go moles to liters. That's the base solution, right? And then we can go to, it now doesn't say what volume, but we're going to want milliliters. So start here and there. I'm going to show you a shortcut. I'm going to do it the long way first, and then I'm going to show you, hopefully it's intuitively obvious to you that we can cut out 2 steps by taking a cute little shortcut. All right, so let's pop this baby. What's our volume? 25 milliliters. So let's put our 25.00 milliliters, and that's the acid solution, right? Everybody agree? Not the base solution, that's the acid solution. If you don't do that, you might end up putting the wrong molarity with that one. So let's apply the molarity. So it's 0.1058. Oh, we got to convert. I should probably read my own game plan. Let's go to liters. So 1,000 milliliters per liter. Now we can use the concentration to go from solution units to solute units. So for every liter of solution, we've got 0.1058 moles of the H3PO4. Right on. I'm going to have to erase this. It's going to get squishy, my friends. Now that we're in moles of the acid, we can go to moles of the base. So 1 for the acid, 3 for the base. So for every 1 mole of that requires 3 moles of that. It's exactly like all the other stoichiometry we've been doing. And then we're going to use the concentration provided of the base, right? So we've got 0.2410 moles of sodium hydroxide per liter of solution. I was 1 segment short. And then we're going to convert to milliliters. 1,000 milliliters per liter. There we go. We'll calculate this out. Do you see, real quick, do you see that 1,000 milliliter to liter conversion? Cancels out that 1,000 milliliter to liter conversion. Those thousands just cancel out. So I'm going to show you a shortcut. We're going to do this exact same problem a second way, but we're going to get rid of those 2 steps. So we're going to go from 1, 2, 3, 4, 5 steps down to 3. Instead of relating the acid to the base by moles from a balanced chemical equation, we're going to relate the acid to the base, the solutes there, by equivalence. All right? That's one shortcut. And then there's a second shortcut we can do, where instead of using concentration in moles per liter, we can do it as millimoles per milliliter. As long as you have the same metric prefix on top and bottom, that number doesn't change. So if this is in milliliters, that solution, instead of converting to liters, I'm just going to go millimoles of H3PO4 per milliliter of solution. Oh! And then I could go 1 millimole of this to 3 millimoles of that. And I could do 0.2410 millimoles of sodium hydroxide per milliliter of solution, and I've got my answer in milliliters, which means I don't need to do that 1,000 to 1 conversion, and I don't need to do that 1,000 to 1 conversion. So there's actually 2 shortcuts we could do. Although the equivalent to equivalent may or may not be a shortcut depending on the problem, but using millimoles per milliliter definitely is a shortcut. So let's do the equivalent ratio as a second example. More examples are good, right? So let's do the shortcut. We'll answer this, and then we'll do it again using millimoles per milliliter for the molarity. And I'm going to show you we get the exact same answer. And if you like that shortcut, go ahead and do it for homeworks and labs and stuff like that, which is great. It's up to you. On a test, if you want to do it the long way, that's totally fine, up to you. But you want to move a little more efficiently on exams. Let's calculate this baby out. So I got 4 significant digits in my volume. This is an exact conversion. 4 there, that's exact. 4 there, that's exact. That should happen when you're doing things using standardized solutions to 4 significant digits, as long as you use at least 10 milliliters in your volumes from your burettes and things like that, you'll have 4. If you use less than 10 milliliters, then you have 3 sig figs, and that messes it up pretty good. All right. So what do we get for an answer here? I get 32.92 vertical dash line, because we got the 4 significant digits, right? So 32.9253 milliliters. That's going to round up. It's closer to 32.93 milliliters of base solution, which is a really good amount we would need for lab. Now, if that had been like 75 milliliters, I'd be like, well, that's more than 50, so I might want to reduce the volume of the acid that I give my students, maybe down to 15 milliliters, so that they use, probably between 25 and 45 mils. That's the purpose of this kind of problem. Well, let's do the exact same thing again. I'm just going to leave the whole board up. I'm just going to erase all this. We're going to redo the calculation. We're just going to bypass the 1,000 to 1 liter conversion. So let me erase the board and we'll redo it again and show you the shortcut, which is totally optional for you. All right, it may seem redundant to you guys doing the same problem twice, but I want you to understand why this is a viable option. So not all professors are going to allow you to do this or even show this to you, but I think it's great. And if you're doing a whole bunch of titration calculations in lab, it's nice to save time. So same problem, same balanced equation, but what we're going to do for molarity, this is also true for normality. We know molarity is moles of solute per liter solution. But if I convert moles to millimoles, right, by timesing by 1,000, and if I convert liters to milliliters by putting so you'd have 1,000 over 1 here and 1 over 1,000 there, the thousands cancel out. In converting moles to millimoles and liters to milliliters, the 1,000 to 1 conversions cancel out, and you get millimoles of solute per milliliters of solution. But since the thousands cancel out, the original molarity number does not change. So a 0.2 molar solution is 0.2 moles per liter, or 0.2 millimoles per milliliter, or nanomoles per nanoliter, or kilomoles per kiloliter, or megamoles per megaliter. It doesn't matter as long as the same metric prefix is in the numerator and the denominator, the conversions cancel out. So since we always use milliliters for our volume, solution volumes in lab, it's easy to use millimoles per milliliter for our concentrations. If it was normality's equivalence of solute per liter solution, well, you could do milli-equivalence of solute per milliliter solution. That gives you, it saves you 2 steps out of 5. That's almost half the time to do the problem. Right? It saves you about 40%. So let's see how we would approach this. You ready? Let's again start with the volume. So we got the 25.00 milliliters. Whoops, my milli's looking pretty bad. So we're starting the problem exactly the same way. But instead of converting to liters of solution like we did last time, I'm going to go, oh, well, that's already in milliliters, so I'm going to write it like this. So there are 0.1058 millimoles of solute, the H3PO4 molecules, per milliliter of the acid solution. We bypassed the 1,000 milliliter to 1 liter conversion. Sweet! And now I can relate these by mole. See, that's a 3 to 1 mole ratio, but it's also a 3 millimole to 1 millimole ratio, or 3 nanomoles to 1 nanomole. As long as it's the same metric prefix, the conversions cancel. So I could say for every millimole of H3PO4, it requires 3 millimoles of base. Right, so I'm just doing everything in milli. And now that I've got millimoles of NaOH, I can use the concentration as millimoles of NaOH per milliliter of solution. Let's do that here. So there's 0.2410 millimoles of solute per milliliter of the base solution. 3 steps instead of 5. And look at how the units cancel. Milliliters of acid solution cancel out. Millimoles of the acid cancel out. Millimoles of the base cancel out. And all I'm left with is milliliters of base solution. I like this shortcut a lot. You'll learn to appreciate it, trust me. And we should end up with the exact same answer, 32.92. If I could write that properly. Vertical dashed line. 5.3 milliliters of base solution, which rounds up to 32.93. Easy peasy, right? I like that. And again, you could do the same thing with equivalence, with normality. You could do milliequivalence per milliliter solution. One more arrow in your quiver, my friends. Let's do another example. But I'm going to show you how to relate acid to base using equivalence rather than moles, and you can skip the entire balance. You won't need a balanced chemical equation. It's pretty slick. Unfortunately, my black pen is running out of ink, and I'm doing these from home. I'm running low. My supplies are running low. So squint your eyeballs there. Here we go. If 32.80 milliliters of a 0.2511 molar sodium hydroxide solution were required to titrate 15.06 milliliters of an unknown acid solution, truly unknown, you don't know its concentration or its identity, what is the normality of the acid solution? So I'm being a boogerhead. I'm not doing molarity here. I'm doing normality. So this is in molarity. Your base is in molarity. Your acid we want in normality. Right? Which is equivalence per liter or milliequivalence per milliliter solution. This is a fairly common one if you don't know the acid. Right? We're going to have to use a secondary way to do it. And this would be our titrant, the base. So it's a standardized titrant. We know the concentration to 4 significant digits. This is the amount of volume that came out of the burette. The 15.06 is probably something we measured from a second burette into an Erlenmeyer flask, added the indicator, and yada yada, we're off to the races. We cannot, can you see we don't know, we cannot relate the acid to the base by moles because we don't know the balanced equation. All right? So we do not know the balanced equation. Hopefully you agree with me because we have no idea what the identity of the acid is. Is it monoprotic, diprotic? If it's monoprotic, it'd be a 1-to-1 mole ratio with the NaOH. If it's diprotic, it'd be a 2-to-1 mole ratio. If it's triprotic, like the last problem, it'd be 3-to-1. We have no idea. So we cannot relate. So we cannot relate the base to the acid via moles. Hopefully you understand the problem here, which means if you can't do a balanced chemical equation, you don't know the mole-to-mole ratio, we can't do what we did in the last problem and convert the acid to the base or base to acid via mole ratios. We have to do it a different way. Good thing about that is we can do it with equivalence. Right? So we're going to relate them through equivalence. Now, you can always relate them through equivalence. If you have a balanced chemical equation, you can relate them for moles. It's totally up to you. You can do it either way. It works both ways, and you get the same answer every single time. But when you relate them by equivalence, you never need a balanced chemical equation, so technically it's always faster. Slick little thing. You don't learn, a lot of places don't teach equivalence and normality, but it's a slick little trick when you're doing acid-base titration, right? So we must relate acid to base via equivalence. Now, this is a wonderful, slick little trick. Mole-to-mole ratios could be 1-to-1, 2-to-1, 3-to-1. Just depends if the acid is diprotic, triprotic, whatever. Right? But when you're relating an acid to base by equivalence, right? And since it's just an H plus going from the acid to the base, and that would be one equivalent, right? Right? Because NaOH is one, that can pick up one equivalent per mole. And it picks up one, the acid donates 1 H plus at a time. The base can only pick up 1 H. You can't have the acid donate 1 H plus and the base pick up 2. That doesn't make any physical sense. It's 1-to-1. Always. It doesn't matter what the identity of the acid or base is. It's always a 1 equivalent of base to 1 equivalent to acid ratio. Always. So if we're going acid to base, use this one. If we're going base to acid, flip it. You could also do it via milliequivalence, or 1 milliequivalent of base So if you're dealing with that other shortcut we showed you, and you can combine the other shortcut doing concentrations in millimoles per milliliter or milliequivalents per milliliter and combine it to 1 milliequivalent base to 1 milliequivalent acid and skip the balanced chemical equation. You can do these problems in less than half the time. Whoa! Life is good. So now that you know this, let's do this problem using these shortcuts. And we have to relate them by equivalence. And since we're dealing with milliliters of solution, let's use milliequivalents per milliliter, millimoles per milliliter, and let's show you how fast we can do this. If you feel adventurous, pause it while I'm erasing this. See if you can do the problem using these shortcuts and see how fast you can do it and build up your confidence with it so you can just scream on an exam. Bam! Done. Did you get it? Did you get it? Here we go. What are we solving for? We're solving for the normality of the acid. We're solving for acid, so start with base. Start with the volume of the base. So we're going to go milliliters of base solution. And let's do millimoles per milliliter. So we can go to millimoles directly. Right? We cannot, now we don't have a balanced chemical equation, so we can't go to millimoles of acid. It's impossible. So we got to go to milliequivalents or equivalents, but let's stick with milli across the board, right? So let's go to milliequivalents of NaOH. And since that's a monoprotic base, it'd be one equivalent per mole or 1 milliequivalent per millimole. If you need to review the video on equivalence normality, I highly recommend it. All right. Well, once I'm in that, I can go to milliequivalents of the acid, which is always a 1-to-1 ratio, equivalents or milliequivalents. And to get normality, that's equivalence of acid per liter of solution or milliequivalents of acid per milliliter solution. So from here, we can go to normality. We're going to take that answer and divide that by the volume of the solution. And you can do it in the beginning or the end. Pretty straightforward. Here we go. You ready? What's the volume? 32.80. So that's the volume of our base solution. Let's use the molarity. So for every milliliter of base solution, there are 0.2511 millimoles of base. Shortcut number 1, right on. Now, since that's a monoprotic, it has one OH minus with a -1 charge. Every millimole of NaOH has 1 milliequivalent. Or you can do equivalents per mole, but we're doing the shortcuts. Now we know it's a 1-to-1 mole, a 1-to-1 equivalent or milliequivalent ratio. So 1 milliequivalent of base requires 1 milliequivalent. Now we don't even know the formula of the acid, so let's just put acid there. Let's take a look at our units. Milliliters of base solution cancel, millimoles of base cancel, milliequivalents base cancel. We're left with milliequivalents of acid. Now what's normality? Normality will be milliequivalents per milliliter or equivalents per milliliter. So we got milliequivalents on top, so we need the milliliters of the acid solution in the denominator. I gave you that, 15.06. So we take that answer and divide it by 15.06. You can do it here. You can go 1 over 15.06. I'll show you both ways to do this. You could squish it here and go 1 over 15.06 milliliters. Then you get the milliliters of acid solution on the bottom. Or, I don't care, you could do it over here. Right? So you got milliliters of base solution there. You could go 15.06 milliliters of acid solution. So you have your base solution on top, which you can convert to equivalents of acid solute over the acid solution. You can do it this way or the other way. I don't have a preference. Okay? Typically, I'll do this. I'll divide by going 1 over 15.06 milliliters of acid solution. Now, normally it's not that squishy on paper, but this is squishy. So whatever your preference is, it makes no difference to me. 4 sig figs, 4 sig figs. This is exact. This is exact. 4 sig figs. My answer is good to 4 significant digits. You should get 0.5468. Vertical dash line. 84 milliequivalents of acid per milliliter of acid solution. Righto? That is normality. This is going to round up to 0.5469. Normal. Look at all those beautiful shortcuts. There you go. This is how you do acid-base titration calculations. Shortcuts optional, right? And I give you 2 different kinds of shortcuts. Play around with them. Have some fun on the homework, and you'll appreciate it in lab. Trust me.